Hello, everyone. Welcome to the Sanctuary Ground Truth podcast. Geordie does a lot of talking today in the episode, so I thought I'd do the intro here so I could have a little airtime with you guys. Today, we talk a lot about data-driven models, and Geordie talks about where a lot of thinking about first-person experience came from a project he was working on at the weekend, which was creating a fully autonomous generative AI-based radio station. Seems a little weird, but I think there'll be lots of interesting discussions diving into physics, data, humanoid robots, first-person experience, and the fun of building your own radio station. Enjoy.
Good morning, Suzanne.
Hello, Geordie.
How are you this fine morning?
I'm good, thanks. How are you?
I'm pretty good.
Mm-hmm.
Do you know what I did this weekend?
Something tells me it involves audio.
Yes, I set up an internet radio station.
Oh, okay, that's cool. Tell me about that. And wait, why? So what motivated you to do this?
What motivates us to do anything, really?
Dopamine.
Well, I'm not exactly sure what got me thinking about this, but I listen to the radio on the way to work usually, and I just started thinking about it. Like I was being mindful about like what actually was going on the radio. So I started listening to the commercials and thinking about how the different like technological parts work. Like how do you run it 24 hours a day? And how do playlists get generated? How do you license music? How much money does a radio station make and all that kind of thing? So I just started thinking about all this and I thought, well, maybe I could make my own radio station and see. So I did some research on internet radio, like not actual like broadcasting.
Yeah, because you didn't like set up your own ham radio station
no.
set up with a giant like coat hanger on your roof.
No, an internet radio isn't actually radio. It's weird because radio is like an actual thing.
Yeah, it would
right?
be more impressed if you'd done an analog radio station because I like analog computing and stuff.
Yeah, I think that might be beyond my
that's
capabilities. I think I might have to enlist your help if we're going to actually build an actual radio station.
Okay.
But it would be interesting to figure out how you do like the frequency licensing and all that stuff. I don't know how that works either.
I think with that ham radio thing, you can join like clubs, and then there's certain, I guess, frequency bands allocated to that kind of amateur hobby radio stuff, and you can just broadcast, maybe sign up for something.
Yeah.
Or you can just go totally underground and have like a pirate radio station that's just broadcasting.
Yeah. What I was thinking is you could, I'm sure there are a lot of radio stations that are kind of struggling to make ends meet. You might be able to buy one for cheap and acquire all of its like people and licenses and all that kind of stuff. Anyway, so I wasn't doing real radio. I did internet radio, which
Brand
is
new Sanctuary FM.
Well, maybe. Yeah. So I used a commercial tool bought through a company that basically does all of the back end work for you. And I think you can actually do it all for free. Like all of the underlying software is open source, or could be, to actually do broadcast radio on the internet. So it's basically like a website, except instead of all the doodads of a website, you're just broadcasting audio. So it's anyway, I went through all of that, and I also collaborated with you a little bit on making content.
So we're going to link this back to AI, right?
Yeah.
Just in case people are wondering why the hell we're talking about radio stations, there is a link here.
Yeah, it's a little tenuous, but it's there. So
I don't think it's tenuous.
Okay, so the link is, I got thinking, could you actually, of all of these things that radio stations do, could you make them all autonomous? So that is create every single piece of content on the radio station on the fly, autonomously, following some templates. So the way that the radio station works is that you schedule different things in different orders. So you got like you play 3 songs in a row, then you go to the live DJ, then you play a commercial and so on. So there's like a schedule thing. But each of those blocks it itself is automatable if you can automate the kind of content that would be in the block. So for example, if I wanted to have a talking head like a Howard Stern or somebody like this that had a show, you could use a combination of AI tools to automate the show. And where for the music, there are certain AI tools that you can use to generate autonomous music. So this is ephemeral music in the way I was thinking of it, which means it's only ever generated and played once, which I find I like that aesthetically, that idea.
That's part of the vaporwave aesthetic.
Yeah, it's the vaporwave thing.
Mm-hmm,
yeah.
Mm-hmm.
And the commercials, this was the most fun part of all of this. And I hope to share this with you guys at some point. So the way I thought about through the commercials is most commercials have a very specific structure. They're kind of like little movies, but they're only like 30 seconds long. So once you understand the structure, you can follow the structure, but generate each of the pieces using AI tools. So I generated music, jingles, jingle text, and the body of the commercial. And the way I did it is I first asked GPT-4 to give me a random product name for a product that doesn't exist and a random company name for a company that doesn't exist. And then I asked it, what 3 features should this product have to be useful? Then I asked it, convince me to buy this product in 20 seconds or less of text. And then it would generate the text. So the way the commercial worked is there was some music that was generated by Meta's AudioCraft program that started it, completely random, but conditioned on the product. So the way that AudioCraft works is that you send text in and you get music back, or sounds back in some cases. So I asked it to generate music that would be the commercial entry for the product, and then I filled in the product name.
Is AudioCraft a free resource?
Yeah. AudioCraft is open source.
Do you need a Meta account? Or?
No, you just need to download it from GitHub and run it. It does require a fairly beefy GPU, but I have a 4090, which is the thing you need is the memory.
Tell us about your GPU specs.
Yeah, so I have a fairly, I guess when I bought it, it was a high-end like a stock user. Like you're not actually doing fancy stuff. It's just like you can buy these things. GPU. And the thing, for those of you who don't like train or do inference on neural nets, the thing that matters in the GPU is actually the memory that it has, because you have to be able to load these models into the memory. And so it's not like the 4 or the 3 or the 90 or the 80. It's actually the memory. So there are certain GPU cards that look like they're really fancy, but they actually have lower memory than the ones that are higher. So you just look at the, anyway, I've got a 4090 Ti, and it's got enough memory to run most of these models, not all of them. Anyway, so I ran it locally on my system. So what it will do is it will generate on the fly. Again, these are on the fly ephemeral commercials only meant to be played once for a product that you can intersperse with the auto-generated music, like actually building songs. And you can also generate text, for example, for like a talking head. And the last piece of information I'll share before we move over to something that is more directly relevant is that we cloned Suzanne's voice using Microsoft Azure voice cloning. And we used Suzanne's voice to as the voiceover for all of this. And I actually have...
It's called Custom Neural Voice.
Yeah, we did.
It's part of Speech Studio.
Yeah, we did the one that's called Light.
Mm-hmm.
So it's not the best one because we were just playing with it. But I'm just going to play you some just through my phone. This is like the most analog thing ever. But I'm gonna actually
totally not going to.
I'm going to take my phone and I'm going to hold it up to the microphone and we're going to see if
have to edit up this afterwards, you know.
Okay, well, whatever. Let's see if it works.
The second aspect of my philosophy is the concept.
Whoops.
You stopped it. Also, you're showing everyone your phone screen.
Oh yeah, you're right.
This is the idea that true peace, understanding, and enlightenment can be found in the here and now, not in the past or in the future. Our minds often hold us captive, making us prisoners of our past or anxious about our future. We ruminate over past mistakes or fear potential future problems, denying ourselves the beauty and peace available in the present moment.
Anyway, I thought that was pretty good. So that's not Suzanne's
I
actual
just sit
voice.
here and not talk anymore.
Yeah, so that was GPT-4 generating some meditations in the style of Eckhart Tolle using Suzanne's voice.
So you mentioned you used GPT-4. Have you noticed any improvements over GPT-3? Because last time we spoke, you were using GPT-3 or 3.5.
I didn't do enough to know, but
is it still getting better, do you think?
Well, it depends who you ask. A lot of the internet and people who do testing claim that GPT-4 has actually degraded significantly in its quality since it was launched.
Because of all the RL stuff?
Yeah. Because it's safe
for
modern audiences.
If you reduce the training set, it's not going to have as much data. And I think they're just chopping giant pieces out of the data manifold now.
I don't know if they're chopping. It's more like they're hiding because it's still there. It's just not being sourced in the inference. By the way, on a related note, I downloaded and started playing with the Llama model, the Meta one. And
is that Llama 4B?
No. So this was
7B.
It was the Llama 2. And the two models that will fit on my GPU that I downloaded were 7B and 13B.
Okay, 7B. Yeah.
The other one was 70B, but that was that.
You can fit 13 billion on your GPU.
Yeah. You have to start worrying about bit depth quantization, like how many bits you use to represent the weights.
Interesting.
At that point, but the thing about
Wait, what happens if you... Okay, this is fascinating. What happens if you just truncate the bit depth on all your weights? So you're essentially moving towards something that's more quantized. What happens to the inference in the model? If you just...
Well, the two obvious things is you require enormously less memory and it's faster.
But does it degrade the quality?
That is an extremely good question.
Like, could you take this to the extreme and make them binary?
Well, you know who's worked an awful lot on that particular problem. Let's say it's complicated. So the reason it's complicated is that you're of a trade-off. So the more bits you use to represent a number, the more expressivity that number has. Okay. So you can, quote unquote, store more information. But the point of doing these neural net training is not to store information, is to generate inference in the style of the data. And there's a thing called regularization in machine learning, which is a process whereby you try to learn the underlying structure of the data, not the details. So if you give a model more expressivity, more power, it can memorize the training data, which isn't what you want. You want it to learn underlying patterns of things. So in particular in language, where the tokens are discrete and have low bit depth themselves, it's not clear how many bits you need to strike a good balance. But the ones that I was using were 4-bit, which is really low bit depth. Usually when you're using your computer, it's 64 bits or something like that. But 4 bits seems to be enough. But I didn't really do any systematic experiments. I was just like, I was lol, make GPU go burr.
Yeah.
Like it wasn't.
Well, you're not really regularizing it. I was thinking more at inference time. So obviously you don't reduce the bit depth at training time because your back propagation won't work properly.
No, it will.
Really?
Yeah.
If it's like really low bit depth?
Yeah.
I mean, it can't find the gradient.
No, there's still a gradient because it's the gradient in the when you change the weight's effect propagates back to the output. So there is a gradient. It's just that the gradient becomes coarser as your bit depth goes down. So it's more like it becomes like a lumpy, steppy gradient instead of a smooth gradient.
Yeah.
And at the limit where you've got 1 bit, you're in binary land, and the whole thing breaks. But with 4-bit bit depth, it's approximately smooth.
So if you lower bit depth at training time, you'll probably get some nice regularization. But if you just train with like high bit depth and then you truncate at inference time, then you'll probably just get a sort of lossy version of the model.
Yeah, I'm not sure.
I'm thinking it's like JPEG compression. It's like if you truncate at inference time, then you've kind of taken your JPEG compression down to like level 6 or something instead of 10.
Yeah, I'm way out of my technical depth here.
Well, you can do an experiment, right? So you can truncate the the number of decimal points or whatever decimal places in your weight. Just keep taking one off one by one, and then have some test output of the model and see. What I imagine is it'll start sounding choppy and kind of like crappy audio. But that would be an interesting experiment to do.
Well, with audio is a different problem set. Like this is Llama with text.
Oh, this was text.
Yeah.
Oh, okay, that's interesting. Well, it'll probably start making typos and things.
Yeah, I don't know. I think
with audio you'd hear it. I think with audio you'd hear the quality reducing as you moved towards.
It's a complicated problem because in audio the tokenization problem is fundamentally a different one. So when in the Meta Audiocraft system, that one of the main innovations that they released was something they called encoder or encode, something like that, which is a neural audio tokenizer. So the a token is a symbolic description of something, and audio is highly naturally analog, let's say. So it's got it's a wave in one dimension.
Neural tokenizer sounds like dictionary learning.
I think they used a related thing called vector quantization, which you might remember we did a little bit of a couple of years ago.
VQVAE.
Yeah. So this was vector quantization is very strongly related to dictionary learning, but it's not exactly the same thing. Anyway, the way that the tokens are represented and the way the neural encoder and decoder work convolve two different kinds of bit depth discussion. Anyway, we're getting way off topic here.
I like these kind of discussions.
Yeah. Anyway, so coming back to the internet radio station. So we built a prototype where the kind of text that I was just flashing and some of the music.
But the
stuff
Llama
too.
model was separate than the station, right?
That was totally separate.
Okay,
I didn't use Llama. I used GPT-4. Just dummy scripts.
Are you going to try the same thing with Llama to see if you can have a fully home rolled source code system?
So the only advantage from the perspective of this project of using Llama is you don't incur the costs of running on the GPT-4 system, which are very small. Like my monthly bill for OpenAI is like $5 or something. Like it doesn't cost very much.
Wait, there's another. Can you find? I think you can fine tune Llama.
Yes, you can.
That's another advantage.
And the other thing, which is an interesting thing, again, I didn't explore. Llama doesn't have all of these safeguards on it. So I don't think anyway. I think you can use it to generate something that's more akin to what the raw model would output.
So we can make it spicy.
Yeah, or you can make it spicy, or you can get more interesting results. Let's say, because with OpenAI, the way that they've done it, it's really narrowed its use to very specific use cases that are boring ones. If you want to use it for something interesting, you usually get this weird, boilerplate that everyone's seen as an AI model.
Yeah, I cannot say the something about this something.
Yeah, and then you have to go through gymnastics in your prompt to get it to do what you actually want.
Yeah, okay, pretend that you've never been RL. What do they call it? That step.
Reinforcement learning with human feedback.
Human feedback adjusted. What would you say if that hadn't happened?
Yeah. Or when I was asking for it to give me recommendations for how this product would what its features would be. It says, as an AI model, I don't have up-to-date information about this product and blah, blah, blah. And I was like, whatever. I have
You can
mixed
also say
feelings
things
about,
like, describe this in the style of a radio commercial from the 1960s or something to try and like,
yeah, that's a good idea. Actually, I didn't go that far, but anywho, we the TLDR of all this is that in one weekend was really one full day of work. We built a fully automated radio station from scratch, which is pretty amazing. Like it doesn't because I didn't hook the whole thing up, but it would run 24 hours a day, fully synthetic generated content.
Woohoo, you get to listen to me talk for 24 hours a day.
Well, we'd have to add some more personalities, I think, into the mix. Like the obvious next thing would be to do your proper voice clone with the actual professional one, and then do mine as well. And then maybe do a couple more people, and then have like segments. So I could be a Baptist preacher or something, and I could do like the Christian radio, which by the way I quite like.
The evangelist kind of,
So we would do like,
cool.
do that for like a segment, and then we could do
my meditations
for a segment, and then we could do, something about the history of music.
I was thinking we could combine it with the llama stuff. So if we could fine tune a llama model on like say journal entries, we could have like Suzanne's stories section. And
Suzanne's story hour. We could just do an hour of you telling stories about your life.
Exactly.
I'd listen to that.
I'd listen to that.
Yeah. I think this is actually a really good idea that probably somebody else has already done like 1,000 times, because it was so easy and it's so obvious that there must be lots of this already.
I want to talk a little bit about this side loading thing, because I know we talked about it a few episodes back, and in my mind, it's always been something that's been a little bit sci-fi and sort of a fancy thing that's not really work related. But as time goes on, it's becoming more and more and more possible. And not only possible in principle, but we can actually do parts of it now pretty well. So I'm wondering at what point we'll be able to take a person. It doesn't have to be me. I just like, the reason I do this with myself is because I own and control all my own data. So I'm not hitting any privacy concerns or anything like that with my own. I volunteer my own data. So imagine now if we took like this clone voice thing, we took like a fine-tuned llama model for memories, and then we hooked that into a cognitive architecture that had a bunch of other information about, say, personality and likes and dislikes. And I think you can weave this in together with the LLM stuff as well, because I think the way to build a sort of let me just remind people in case they've forgotten, when I use this word side loading, it originally came from a Greg Egan story that I really liked, and the idea is instead of mind uploading, where normally that involves some kind of brain scanning, you actually just offload all your data into a computer model via more traditional techniques such as writings, photos, this kind of stuff. So it's like a non-invasive mind cloning technique. It's called side loading. So I think side loading and cognitive architectures and LLMs go together naturally, because you can have your LLM fine-tuned, but then it can also, as part of the system, if it determines that the answer needs to be, say, something like a specific memory, it can then query a database of journal entries, pull out the paragraph that had that specific memory in it from that date, put that into the prompt. So one of the things I've always wanted to do is to have one of these like fine-tuned LLM models, but also have it able to create its own prompts by querying databases and other sources of information. And I think that would be a really cool way of creating like a side load of a person. Where I was going with this is you can do all that, but that's kind of on the voice and the speech and the like conversational side of things. But we can also do this with the robots now as well. So we're setting up internally at Sanctuary, we're setting up like a data pipeline project. So we're able to gather tons and tons and tons of data coming off the robot and the teleoperation systems and store all that, annotate all that, and automatically tag it, and then be able to train essentially behavior cloning models on those data.
So this was the actual meaty topic I wanted to talk about today.
Sorry, I'm preempting you. Sorry.
We got into my.
Wait, let's finish the radio station thing first, and then we'll come back to this because it's very interesting.
Well, the immediate link, which is a superficial one, but it's actually quite important, is that voice cloning has gotten so good that we can run any voice on the robot now. Mm-hmm. So the robot can speak with any voice we can clone. So what we're going to do is hook up the Azure voice, your Azure voice, to the robot, and you're going to be the voice of the robot. At least we're going to do that experiment. And then as people may want other kinds of voice for the robot, one of the services we're going to offer is to have the robots have whatever voice you like, as long as we can legally clone somebody's voice or use an existing licensed voice, we can put it, the robot can speak in whatever that voice is. But initially having it be Suzanne's voice, like you say, avoids all of the licensing issues. And
when you do this voice cloning thing, you have to kind of jump through quite a lot of hoops to actually have it happen. You have to make sure you have the rights to use the original data. You have to do a kind of interactive audio voice verification process where you actually have to speak a certain phrase so that the system knows that you own this data and you give consent and things like that. So it's not like it used to be where you just pull audio off the internet and clone someone's voice. No.
Well, you can, if
but
you
not with
knew how to
services
do
like
it.
This.
Yeah. And I've tried using some of the publicly available voice cloners by like downloading them and running them. They're nowhere near as good as the pro things now. There's like hidden art now in this
that Azure one is amazing. So like Geordie was saying, I just did the light version, which is kind of like a trial. You can be like, here's roughly what it's going to sound like, and you have to give 50 samples. So basically you read out 50 sentences into a good quality microphone on your computer. You don't even need to record it offline. You just do it straight in the app interface, record 50 voice samples, and then hit go, and it trains the model. And the output from that model, I think, is really good. Like, you can tell it's not me. It gets certain words wrong. Like, it says, especially the word past, it says it like past, which is not. So I think what's happened there is it didn't have enough training data, and it's using a baseline model of like a British accent, but it's using more like the Southern English accent, which would be like past, like the past and the future. Whereas I say past and future. So it doesn't get that. But you can hear those little problems in it. But
I didn't hear that myself. I mean, my problem.
But you'd probably only hear it if you're from my region of the UK, because I would never say it like that.
I mean, my problem with it is, like we've discussed, it lacks the. I think it's because it's the light one. It's lacks certain part of the spectrum. It's very tinny.
Mm-hmm. Not enough bass.
Yeah, it doesn't have the full richness of the full spectrum. So I think they've like somehow only represented certain parts of the spectrum in the light model.
We could run it through a nice EQ in real time.
Okay. I looked at it.
Of course you did.
Well, I just used Audacity. I did a spectrum of it on Audacity because I wanted to see if it was actually clipping the frequencies, and it is. Anyway, okay, so what I wanted to talk about, the meaty topic, was
I like meat.
Yeah, was related to the so those of you who are in the machine learning world or the AI world may remember that there was a paper called "Attention is All You Need."
A very seminal paper.
Yeah, there was the one that kind of started off the Transformers revolution, and then actually you met one of the co-authors recently, the Cohere guy, Aidan Gomez. I think.
Yep, hung out with him.
Yeah, so that was followed a few years later by a Reward is All You Need, which was the kind of reinforcement learning rebuttal, and Rich Sutton was on that paper, and a bunch of other folks from DeepMind. And I wanted to kind of tell a story about the second one and my reaction to it. Because I think it's important to understand this data pipeline that you talked about. So, as we've mentioned before, both of us were professional physicists for a while. We studied physics as kind of in our formative years, and physics has this framework, I suppose, about understanding the world that Sean Carroll has called the Laplacian framework. So the way what this means is that, let's say you knew everything about a system at a given point in time. The way you think about what happens next is that there's a bunch of rules that cranks everything forward like a little bit, and that gives you a new state of the universe, and then you use the exact same rules and you crank it forward a little bit more, and a little bit more, and a little bit more.
And this works both in the Newtonian sense of the term, but also in quantum mechanics, as long as you're considering the entire unitary wave function, right?
Yeah. So if you think about physics in the sense of how do you actually use it to calculate things, this is almost always what you do, is you start from a state, which is some descriptor of things, and then you apply these rules. And the way the rules work is they're literally like a grinding machine. You turn the crank, and what you're grinding is forward in time usually.
But you only ever get out the probability distribution in quantum mechanics, right? And then it's, if you actually want a measurement, that's where all the issues come in.
Sure, but that doesn't change the underlying picture, that there's something that kind of grinds forward in time.
Yeah. I guess it's just like in quantum mechanics, you're grinding forward.
Forget about quantum mechanics. Okay. We don't need to talk about that. Let's just talk about the classical world.
Okay.
There are things, and these things change, and the way that physics uses the word, what the word change means in physics, is that you apply rules to what you have now to what you will get a little infinitesimal time in the future, and then you just keep doing that. Okay, so this is a really important idea. It seems maybe obvious if you think about it. So how is this related to building AI systems? So the reward is all you need premise is that is really intimately connected to this. So I want to say something that might be obvious to everybody, but maybe not. So where we are now in time, like right now, you're listening to this or watching this show, podcast, whatever this thing is. You have it in your mind, and it's probably correct, that there's a thing called the past. And the past was a sequence of these tiny little moments that led up to the now. And the now is what we're experiencing in the present. So this is every moment is the now, but we're accumulating the past. And the past happened, like it was a specific thing that you could, in principle, have written down or taken video of or whatever. You know, there would have been ways to record it, at least in principle. But the future is not like the past. So forget about all the advanced physics weirdness of general relativity and the classical theories where everything is deterministic. Forget all about that. From our own perspective, the only thing we have access to is the influence of the past and the present moment. Okay?
How do you know the past? Because you can't measure that either.
Well, you can measure the past. You record it, and then you go back and look at the recordings.
I guess if you have a good enough measurement to capture.
Okay, so here's the point. If I'm a mind in the world, then in principle, all I have access to is the past and the present. The past already happened, and the present is happening. So all the reward is all you need paradigm says is that every single mind that has ever existed and can ever exist has the accumulated information of the past, which is fixed and never changes, and the moment of the present. That's all it ever has is. And
doesn't it use its prediction of the future to
forget
calculate?
all about that. That's about action. I'm talking about like what it actually has access to about the world. So all it has access to about the world is a bunch of memory about the past and the thing that's happening now.
But what if in the past?
Let me finish.
Okay.
So in the present moment, your senses are receiving data. That data contains a bunch of stuff, and you can call some of it reward. But the formative idea, the underlying idea of reward is all you need, is that any entity at all ever only has two kinds of information: things that have already happened and things that are happening now. All reward is what is happening now. So reward is another word in reinforcement learning mathematical terms for a property of the now. So the thesis is, if you go back to the beginnings of life on Earth, when the first spark of life, ignited, every single chain of living thing from then to now has only ever had the now and the past. So if you think about like what this means for you as a person, the memory of the past is not just the memory of your past. It's the memory of the past of all of your ancestors tracing back to the beginnings of life on Earth. So this is what's sometimes called your evolutionary history, or the thing that you are. So you are a thing that has inherited the memories of millions of ancestors going back billions of years. You are also the sum of the experiences that you've had during your life. But every single part of everything I just said arrived in a now that swept between then and the period of time that we're at now. So all of it is a summed over set of nows. Okay, so the thesis of reward is all you need is that the now is the signal, which is coming from the environment, that tells you whether things are good or bad. And all you need to do to recreate intelligence of the human sort is recapitulate the nows from a billion years or so ago all the way to now in the same kind of environment, and you'd get something like a person. Well, you did, right? We have the existence proof because we're here, and that's the way that it happened. Mm. Okay, so the reason why this is such an important and difficult idea. So I'm sure that most folks who hear this the first time don't really get how fundamental this idea is that the interplay between the way that the physics worldview works, the psychological or philosophical perspective that all there ever is now, and the mathematical side of reinforcement learning, which is how the actual mathematics work, which requires the now as being the primary thing. So there's also accumulation of nows, which is called state representation, but the primary signal is the now. That whole business is very strongly related to something that we're doing here. Okay, so now let's shift gears. If you wanted to build a now machine, a machine that collected experience, so you right now are experiencing your body, you're experiencing the world. There's like a thing that you are immersed in that you're receiving data from and you're moving around inside and affecting. How would you collect that data? Well, the answer is very simple. You don't have to be a rocket scientist. You have to build a machine that's immersed in the world the same way we are, that has the same senses we do and has the same actions we do. It's called a humanoid robot. So I think that one of the things I wanted to get across when talking about this is that often when people talk about humanoid robots, they completely miss the point. The reason you build humanoid robots is not because they're good at work, and it's not because they can carry totes from place to place, although they can do those things.
It's because they're now machines.
It's because they're now machines. They're machines for collecting experiential data, the data of the now, and then accumulating it. And you can build, say, 1 million of these robots that are accumulating 1 million nows every now, and you can store it. So the now data accumulates,
And what is now data? It's vision, like what the robot's looking at, what it's hearing, where its body is in space, which is called proprioception, what it's feeling, which is haptics. And you just collect all the nows and you store them through the robot.
So it's like you're making the Akashic records
Yeah.
for real in our reality.
That's right. That's right.
And we're storing them all in the cloud, right?
Yeah. So we have a project launched now, and the thesis is simple. You collect all of the experiential data, first-person experiential data from all of the robots that we've got. You store it, curate it, and then you use it to train algorithms that are very similar to the way that the current next token prediction models work. Instead of what you're predicting is not the next token or the next piece of audio, you're predicting all of these data streams, vision, audio, proprioception, and haptics. You're predicting the next step, just like physics does. But the difference is, now that I'm an actor, predicting proprioception means predicting where you will be in space. And in a robot, you can just send those predictions to the actuators and it will move. So just like the thesis that our brain predicts where we will be and then we move to the predictions, you can do that in a robot. So our thesis for how you get to AGI is you collect experiential first-person data from a lot of robots doing a lot of broad things, and then you train next token prediction models over all this stuff. And the wonderful thing now is that we're talked a little bit about audiocraft and neural tokenizers for audio. There's an understanding now of how do you tokenize general data types like audio or haptics. By the way,
first-person experience.
Haptics are just like audio.
Yeah.
Haptics are, they're less complicated than audio in some ways. They're one-dimensional streams of data per sensor that are temporal. They have a time dependence. And the interesting thing about all of this, let's go back to audiocraft. So audiocraft has a thing where you can type in text and it will generate a sound, like a cat meowing, and then you'll hear a meowing cat. You can run it backwards. You play the sound of a cat meowing and you can create the text, which is the label, a cat meowing. Okay, so if I'm a robot and I'm out in the world and I hear something but I don't see it, the concept of what it is can light up in my brain. That's a cat meowing. And if the more senses you have, the more of these kind of fusion opportunities you have for taking the full sensory experience of being immersed in the world and creating rich representations of the world the same way we do. So you don't have to see the cat, although that might help. You just hear it and you know it's there. And that sounds like, okay, well, why would you care if a robot can hear a cat? Expand now this to the full range of the experience of the world. So for example, I keep hearing a drilling sound, okay? Now, we just naturally as people make these complicated inferences. Like if I hear a drilling sound, there's probably people drilling. Why are they drilling when they said they wouldn't? Because we told them to cut off at 9 a.m. or they were going to get a fine. Should I now text, Jazz to make sure that, they actually do get fined for their drilling?
Also,
so all this stuff just lights up.
Sense of fusion happens as well. So you imagine, you hear the drilling sound, the kind of phrase in your mind, a natural language phrase, a person is drilling upstairs, and then you also now visualize it. You imagine a guy with a drill in high vis drilling into a concrete wall. At least that's kind of how I'm imagining it.
You visualize
kneeling down, drilling into a concrete wall, and you visualize it, and then you tell yourself a story, and then you start having a kind of emotional reaction to it. What does that mean in terms of my goals that I'm trying to get to right now? We're trying to record a podcast with nice audio and there's this guy drilling on the floor above. So that is now hitting on my goals and motivation systems because I'm getting irritated. And that motivates me to want to text Jazz or smash something.
Yeah. So the way that I see getting to general intelligence of the human-like sort runs directly through this idea that you want to collect the
the first person experience data of something very like a person. And I mean, it's one of these ideas that it's so freaking obvious.
It's just trivially obvious that this is how you do it. The problem is not whether or not you do it this way, because you do, right? This is, I think, the only way to do it. The problem is, how do you do that at scale in a way that you can actually support it and make it happen and get to that? It's like this crossing the chasm problem. So the way we cross the chasm is we make the collection of the first person experience also something useful that people want to have happening in the world anyway. So it's a byproduct. So if you have robots going out there doing useful work for people, that is wanted and desired. But now as a byproduct, you get what you really need, which is this narrow stream.
Yeah.
And that will get you the AGI. If you can get enough of it, if you can have enough robots, enough high fidelity simulation of robots, and a good enough data pipeline annotation, and then enough compute to train the model. That's about it.
Yeah.
Everything else, by the way, is a detail. So how you do this, whether you just throw it at some giant end-to-end thing, whether you create a modular cognitive architecture where you're training pieces of it, all that really does is move the needle on how much compute and how much data do you need. You're going to end up with the same thing in the end. So there are some levers you can pull to make it more or less efficient. But really, you'd only need to do that if you have limited compute and data resources, which we do at the moment.
Yeah. How do you feel about the role of simulation in all of this? Like building virtual worlds for robots to get first-person experience in?
Well, if your simulation is good enough, then obviously you would build a lot of those because it's easier and cheaper to build back than real robots. But currently, simulation technology isn't good enough yet. It's getting there. So again, I think it's a trade-off where you need both at the moment. You could probably train a baseline model in simulation and get partway there, but then you would want to fine-tune it on high-quality data coming from the real world.
Yeah. And what's missing from the simulation now to make it like good enough to be able to generate real? By the way, just so people understand this, if you could create a simulated robot, like think of like a character in a video game that was in a simulated world, again, think about it like a video game world, and you were to ask the question, like, what is the data from the perspective of the simulated robot? So what does the robot see? What does the robot hear? What does the robot feel? Where is the robot in the world? If you could do that, then presumably you're limited by compute at that point, because you could spin up as many of these as you could, get around to doing, and generate a lot of first-person data. So why can't we do that now?
So maybe let me frame this a different way, because I think a couple of episodes ago we talked about what's missing from simulation. So people can go back and watch that. But there's a nice way to summarize it, which is this using a teleoperation test. So imagine you put a human pilot into a teleoperation rig.
Yeah.
And that teleoperation rig now controlled either the simulation or the real robot. And the pilot couldn't tell the difference. Then your simulation's good enough. Or it's as good as it needs to be to not be bottlenecked anymore. I mean, because if your hardware is not good enough, then your simulation doesn't need to be as good either. So the better you make your hardware, the better you have to make your simulation. But I think this test, it's like, can the pilot tell the difference? And by how much is sort of a good way of summarizing how good your simulation needs to be. And this gets quite nuanced. So for example, if you're in the teleoperation rig and you think, okay, I'm in the simulation, let's say you're in the simulation and then a person walks into the room and starts talking to you completely naturally, then you're going to have to simulate a person coming into the room and talking completely naturally in order for the pilot not to be able to tell the difference. Because if a person never, ever entered a room ever in the simulation, then the pilot could probably tell. Especially if you're in a busy environment like a coffee shop or something and there's no other people, it's a bit of a clue that you're in the simulation. So I like this idea of this almost like Turing test on the pilot side. Can the pilot tell the difference between sim and reality? If not, you go crazy on your sim. You've got a good enough sim, then you can just start spinning up thousands of them, collecting enough data. And I think the other thing about simulation is, I think it's all wrapped in, though. It has to be able to run fast enough for you to gather enough data. You can run it faster than real time if you want as well. But even if you run it at real time, if you just spin up thousands of parallel instances of it, you can collect all the data you need.
Yeah, I mean, I've heard this said a few times internally here that it needs to run faster in real time. I don't think that's true, because you have a trade-off versus parallelism.
If you run it faster than real time, then you don't have to pay as much money. Because say it runs
money
twice.
ain't no thing, girlfriend. Just tell me how much we need.
Okay, I will. Yeah, because if you run it twice as fast as real time, then you only need, say, 500 instances as opposed to 1,000 instances in the cloud. So you get quite good savings if you can run like 10x faster than real time or something.
Yeah.
Mm-hmm.
Okay. Yeah.
Can we bring this back to the like side loading thing?
Yeah, I just wanted to make the point that the because physics is local in time, the only thing that matters is now, and the accumulation of nows from the past.
Mm-hmm.
So that's all the data that you need to learn how to be a person, is the accumulation of personal first-person experience, the input and the output side, not the inside part. This is a thing that I think confuses some folks, is that from the perspective of data-driven simulation or data-driven modeling of things, you don't have to understand it. What you need to have is input and output pairs. So for example, if I want to understand how to classify cats in images, I need pictures of cats with labels that says cat or no cat. I don't need to understand what a cat is. I don't need to understand how the picture works. I don't need to understand anything about the world.
I'm not sure I agree with you on that. Well, I disagree.
Oh, come on. It's just
what
do you mean?
Well,
it's a fact.
Right, but there's something you're forgetting here.
What?
So, okay, data in and out, absolutely agree with you. You need to store that. But there is another thing that happens inside the model, which is where we switch our attention to when. And I think you actually need to store that, because that's where our first person subjective experience comes from. So you could say, well, it could be anything. If you just have data in and out, how do you know at any now which part of the model manifold is being experienced? Great.
But you could argue the same thing with the pictures of cats. I mean, there's no sense of what am I attending to in the picture of the cat. It's just a bunch of pixels, but it still knows, the model, quote unquote, knows.
Right, but the most important thing to us is what we actually experience in the now, which is more than just the data that's coming in and out. Because I'm throwing away 99% of the data that's coming in and out right now.
You are in the cat picture too. I mean, most of the pixels in the cat picture are not a cat.
I mean, you could argue that somewhere in the model is also stored how the attention system works, and therefore you don't need it if you have all the nows, because it will be implicit in all the nows.
I think that what will happen...
Do you understand what I'm saying, though?
Yeah, I think, though, that the way I would think about this is that the machinery for doing proper prediction in the kind of data we're talking about will have to have attention mechanisms in it, just like transformers do. And, I mean, that was the whole point of attention is all you need, right? The reason transformers work well is they had this novel way of determining what about the past was actually significant to making the prediction. So in our case, there's going to have to be the same attention mechanisms, but that's kind of a detail, I would think, of the way the models would be structured. The content is the data. The data is the key to this, because over time, the models will evolve and get better and better and better at what they do. And my thesis, which I think I agree with you on, is that the models will evolve to look a lot like the way that the human brain is proposed to do it. Because this is a very human type of data that we're talking about. This isn't arbitrary general intelligence. It's how does a human body move through the world. So the human brain, it's the organ of movement. That's what it does. So the way that the human brain moves the body around the world is going to be a good way to do it.
So when we learn these models, they're going to look like the way that the brain does it, I think. Like they're not going to be some weird alien thing. They're going to be brain-like. There's going to be visual processing like happens in the brain. There's going to be audio processing like happens in the brain. There's going to be motor cortex like happens in the brain. And eventually you're going to stare at this thing and say, hey, that's a cognitive architecture. Even if you started from an end-to-end, solution, and you're going to say, hey, there's this repeating block that happens over and over and over again. Hey, wait, that's like a cortical column. It's going to end up looking like that eventually. But all of this stuff requires data, and it requires that people who are in the AI and machine learning communities understand the premise, which is you want to build something that has general intelligence of the human-like form. You have to learn from human-like first-person experience data. It's not good enough to use text. Text is a proxy. So our first-person data experience of the world contains text because we hear it and we read it, but it's only one very frail modality for describing the world. Most of the way that we are immersed in the world is touch. If I was to pick one sense that was to distinguish the sense of self, like what makes us people, it would actually be touch. It wouldn't be vision or audio or anything, because touch is the thing that allows you to differentiate yourself from the rest of the world. It's the outline of your body. And it's the way that we interact with the physical world.
So okay, here's an interesting thought experiment, or maybe a hypothesis. So you're saying that just given first person experience coming from this embodiment that's human-like, you can like retrospectively create something that evolved, or that looks like the way we evolved to be. So here's my straw man argument. I don't know if you can do that, because the way all the now data that accumulated over evolutionary history was from different kinds of embodiments as we evolved. So there's a fundamental argument against this end-to-end learning approach that creates something like the human brain, because the data that resulted in that end-to-end model existing was not just coming from something that was a human-like embodiment. It was like an integration over, millions of years, if not more, of different kinds of data. So here's where I think a cognitive architecture approach might be superior. So with a cognitive architecture approach, you're making decisions about the kind of priors that evolved in the model. So you're not using any of that historical data, but you're saying, this is how I think the model was structured from all those different embodiments leading up to this point. I'm now going to intelligently design that in. From here on in, I'm now going to, whatever you want to call it, fine tune or continue to change a model based on the modifying the weights of learning over lifetimes, or at least over the evolutionary history of since we were human-like, right? So this is kind of quite a deep and nuanced argument, but it might be an argument against the end-to-end learning approach, creating something human-like. And if anyone can follow this and understand it, please come and work with us.
I completely
do you get
agree
the
with
argument?
you.
Yeah.
That in practice,
so maybe reward is not enough.
Well, it is in the evolutionary sense. I mean, the point of reward is all you.
Nope. Because it's a reward from a different.
It doesn't
system.
matter.
The IO is changing over time.
The argument of the reward is all you need paper is trivially obviously true, which is that you are the sum of a bunch of moments in time. That's all. All it's saying is that every living thing tracing back to the beginnings of life on Earth, all of your ancestors only ever had their past and the present.
But how can reward be enough if your learning signal is always coming from the same data type, from the same embodiment?
It's not in biological systems.
No, but I'm talking about if you want to build something.
That's different.
Right, okay. Let's make sure we're talking about the same thing.
So reward is all you need is a statement about biological intelligence.
Okay, I understand that. But people also use it to apply to end-to-end learning, saying that all you need is a giant model and data and a reward signal. That's how I interpret that paper. And
no,
you can build anything.
No. The paper was about biological intelligence.
Okay.
Because it's trivially true unless you can go, you can time travel.
I mean, I don't think that's
reward
even
is all you
interesting
need.
to talk about because it's obviously true.
It is an interesting observation, though. It's just pointing out something obvious, that if you go back, say t equals 0 is the spark of life on Earth.
Yeah.
Okay. And then we start stepping forward in time. That little, whatever the hell it was, self-replicating molecule or whatever, even precursor, all it has is the now, right? So t equals 0. It's got nothing.
I understand what you're
now
saying.
It's got now.
I know.
So now it's t equals 1.
You went over this. She talks about this for 15 minutes.
Yeah.
And I get it. It's like, but what's new? Like Charles Darwin talked about this.
What's new is that process derived general intelligence. So it's clearly true that reward, in the RL sense, is all you need to get to general intelligence, because we have an existence proof. We are the result.
Okay.
So that now there's I understand there's a totally different question, which is that a practically useful piece of information for folks who actually want to build general intelligence?
Mm-hmm.
And I think it's partly useful, but not in its full bloom, because you're right. We don't have the compute resources to recapitulate the entirety of evolution of life on Earth, because that's billions of years. We can't do that. But what you can do is start, like you say, from an intelligently designed backbone. So we try to figure out, what does our evolutionary heritage give us in terms of machinery? So start there, but then fill in the blanks with the data. So for example, how does a person motion plan to pick up a cup of coffee? So we don't know how to do that from the perspective of hard coding in evolutionary priors.
Well, that's not true. I think we do.
How would you do it?
Well, we know some ways about how to make motion planners work in robots using like optimization algorithms or, geometric approaches. So that's hard coding in priors. We're saying we know how to solve a sort of 70-dimensional joint space trajectory optimization.
But you still need data.
You actually don't need data for that.
I think you do, if you're going to do it in general.
No, you can do it fully generally just using optimization approaches. Now, whether you would or not, because they can be slow, you have to kind of like reduce the dimensionality of the space and stuff. It's probably easier just to do a neural thing. But I mean, if you're looking at ways in which you generate data to train a neural model, you actually tend to have to do things like those classical planning approaches to even get the data in the first place to train the model.
Well, you can use teleop.
There's not enough data.
Well, that's a different problem. Like, yes, it's hard to get data, but that doesn't mean that it's not the goal of all of this.
Can I just come back? I just want to like poke and pick at this point a tiny bit more. This thing about reward is enough. I don't think it is, because the reward is enough even in the biological sense. So I'm not even talking about the machine learning sense now. Even in the biological sense, you have the environment. You have priors about physics and the environment that we evolved in. Those are what ended up generating general intelligence. If we just had a perfectly, featureless, 5-dimensional, like white room or something, and you have reward, you're not going to generate general intelligence. So I don't think reward is enough, right? The environment was given to us specifically, and I think most of the intelligence that evolved is a function of the environment, not the reward system per se.
Yeah, but that's not the claim. The claim wasn't that reward is enough for any environment. The claim is that the reward was enough in this environment.
Are you sure about that?
Yes.
I don't know. I think it was broader than that.
Well, I mean, there might be extensions, but you can also always think of edge
reward
cases.
Plus this specific is enough. I'll give you that. This specific physics.
The thing about this is that in one way of looking at this, which is the way I interpreted it, this is not a controversial statement. All it's saying is that the time is, our time is local. That's all it's saying. So you can't see into the future, essentially, is what it's saying. Mm-hmm. So if you believe you can't see into the future, then clearly the signal that you've got today, the data that you're getting now, is the only thing that matters, mm-hmm. which is true. I mean, it has to be. And there is no way around this. So the question about like, what does the data need to look like in order to generate over the passage of eons general intelligence? That's another question. Mm-hmm. Because if you'd have to have an environment that was rich enough to be able to spark life in the first place. Yeah. And ostensibly support it, it would have to keep going, because if it didn't, then, whatever. So there's a question about what does it mean to, like, it's one of these anthropic principle things, is that if the environment was sufficient to support the evolution from the beginnings of life to, a biodiverse planet, is that enough? I think probably yes. And it was in our case anyway. So like a little bit of an anthropic thing, I think, is that we clearly are evidence that this is true, at least for one, set of physics.
So maybe just to go back to the sideloading thing. So we think we can do this for specific people as well by teleoperating the robots, right?
Yeah, with the caveat of this, can you actually build a model that integrates enough of the past mm-hmm, mm-hmm. without having experienced it?
Yeah.
That's the evolutionary heritage part.
So that's why we need a cognitive architecture.
Yeah, it's a way to kind of mimic the process of getting to when you were born. Mm-hmm. Mm-hmm. So all of the billion years that preceded you baked into you when you were born a whole bunch of the past.
And if someone wants to create an end-to-end model that captures all that up to that point, I'd be happy to use it.
Well, you can't. Even in principle, that wouldn't work, because evolution is not directed, right? If you were to, unless you, okay.
Well, you need to simulate the entire of life on Earth.
Yeah. Unless you're some kind of weird classical weirdo, the physics that we know of is not deterministic, at least, locally. So if we went back in time, if we could, to the beginnings of life on Earth, and we were to run the laws of physics forward again, we wouldn't be here. Like, humans wouldn't be here, I don't think, anyway. I think it would be highly unlikely, because evolution would have picked a different path. Like, this is maybe not as clear as I'm making it out to be, because who knows, but I think it's unlikely that if you were to run this, multiple times, you get something like humans coming out as a matter of fact. Although who knows?
Well, maybe we'll see that when we start to explore other places in the galaxy. And if it does happen often, then we'll see a lot of other life.
Yeah. Yeah,
if it doesn't,
true.
Then we won't see any life. Because these millions or billions of experiments have already happened.
I think life is everywhere, but I think it's very unlikely that it looks anything like us.
Right.
Would be my guess.
Interesting.
Yeah. I mean, people have tried to do these kinds of artificial life things, but it's just so difficult, because you need to simulate the full world, the environment of the little creatures, and then it takes forever, right, for anything to happen. Like these timescales we're talking about are so inconceivable to the human mind. Like, we can't even think about how long they are. We have trouble thinking in like hundreds of years. 200 years ago, there was no like cars or electricity. That was like not that long ago.
Healthcare.
Well, we still don't have that in British Columbia.
We're getting there.
Anyway, I think that I'm really taken by this idea of collecting first person experience data and then using it to build these next token prediction models for AGI. I think that what part of the reason why I like it is that there aren't a lot of missing pieces in how you would actually do it. We know how to do it. We can build tokenizers for all of this data. We can do, the kinds of things that you just do with the sorts of data when you're building token prediction models. And then you can run it on the robot and see what happens, first in simulation and then in the real robots.
One of the things I'm really excited about or interested in is how easy is it to clone mannerisms of particular pilots. So you can generally tell if someone if you've seen them piloting a lot, you can tell who's piloting the robot at any one point by how they move the robot. And as the system gets better and better, these movements are going to become more and more faithful to the actual human pilot's body mannerisms. So I love the idea of whether you can actually have a robot move in the same way as a real person, and then couple that together with the voice cloning and all those other things we talked about you can do with LLMs and stuff. And it's like, do you think in a time frame anytime soon we're going to see this not just spark of life in the robot running fully autonomously, but it's like the spark of a particular person? Do you think that we're close to that?
Yeah.
How close? Because
I think it's within the envelope of what we can do now.
Mm-hmm.
Like, I think obviously that's not the same as having done it, but I could imagine how you could. So then it just becomes a matter of focus. Like, what are you asking the team to do? I think if we were to focus the team on exhibiting this kind of real, like, I'll call it behavior cloning, but being very specific.
It's literal behavior. When we say behavior cloning, it's actually
behavior.
A term in machine learning that's a technical term, but it's also an intuitive term.
So it's more like side loading.
Yeah, side loading. Yeah.
So could you build different versions of Carbon that were trained on the data of different people, and could an external observer tell them apart? Yes, I think we could do that now. Or within, a few months, if you put the effort into it. Then the question would be, why were you doing that? Because, limited resources and all that. But it feels to me like the progression to being able to do full side loading, that is building synthetic, that's maybe a different kind of word, but building robots that have the absolute appearance that they're being piloted by a person, like an actual flesh and blood person, specific person, but they're not. That's within reach.
I had an interesting thought on this, like while you were talking, because one of the things that's hard to do with behavior cloning with pilot data is like walking. Because when the pilots teleoperate the robot in its bipedal form, as in when it walks around, the pilot doesn't actually walk. So this is maybe an important point that maybe people aren't familiar with this. So the teleoperation rig, the pilot controls the upper body of the robot, the head, the torso, all that is the robot moves in a very analogous way to the pilot. But you can't do this with walking, because the control loop latency needed for walking is much, much, much faster than a teleop rig would be able to provide. Imagine trying to move your leg, you're moving a rig, it's all heavy, and you just don't have the reaction time, right? So you can't do walking, but there's a cool thing you can do. So we have a motion capture studio here at Sanctuary, and you can actually record people's motions. So you can record them like doing tasks, but you can also record them walking around. And the gait as in the walking gait of a specific person is very, very, a very kind of personal fingerprint. So I don't know if you've ever noticed, if you're like kind of waiting for a friend or something somewhere and you see them coming towards you, you can see them like 8 blocks away. I know it's them. It's amazing because you can't resolve any facial features, anything like that. It's essentially just like a kind of colored blob, but the way they walk gives it away very, very quickly. So I love this idea of using a motion capture studio to capture like someone's actual walking gait, and then use that to be training data into the walking model. So you'd probably fine tune it because you'd have some baseline bipedal walking model that was trained using like a model-based controller or something, but then you can also fine tune it with data from this motion capture. So the teleoperation pilot would sit in the rig, they would take full control of the robot's upper body and torso and head, but they would load in the parameters for their particular walking style when they hit go. And then the way they control the robot walking is they just like press a set of pedals, like gas pedal in a car, robot goes forward, but now it goes forward like them. So it's walking like them as well. And I just think this idea is so cool.
Yeah, that is cool.
You know, another cool thing about sideloading is, do you think a robot would be more trustworthy if it's behaving in a predictable way like a person you actually know? So you're likely to trust a robot more if it's been a sideloaded copy of a specific person that you know and trust, and you are very able to predict what they're going to do next. That might actually be a selling point.
Yeah, I mean, it opens up so many possibilities for...
Because people are always worried about AI. They're worried about what AI might do, how it might react, how it might behave. But imagine if your AI is just a perfect clone of a person that you already know. That is going to be as predictable and as trustworthy as that actual person.
Yeah, but there's a long logical leap that you're making there.
Which is?
Well, that you can actually do it.
We just said we could do it in like 3 months.
No. No, what I said is that you could tell them apart.
Okay.
So if you were running Carbon Suzanne and Carbon, I don't know, Chris, obviously we wouldn't use voice because that would be obviously. Yeah, but if you were just to use the physical movements of the robot, I'm pretty sure you could tell them apart if they were trained on different pilot data. But that doesn't mean that they're exact clones. I mean, that's a light year leap.
Right, but it's just a long tail to get there. You just need more and more and more data.
Yeah, but I think that the thing that's going to be difficult for fully autonomous robots of this sort is it's the thing that we were talking about with OpenAI. Is there are trade-offs? If you want something to be fully human-like and as powerful as it can be, you don't want to put chains on it. You want to unleash it. But when you unleash it, it becomes unpredictable, like people. Maybe more so in this case because we don't really understand these systems.
People are that unpredictable.
It can be. I mean, it depends, on the context and all of that. But like if I was to take a random person, sampled from the Vancouver population, and you had to share an office with them for a day, I don't think you could predict how they're going to behave.
Right, but I think people are inherently more predictable than like random AI systems.
Yeah, that's true. Yeah.
Right?
I get yes, you're right. But I think that the more predictable you make a robot, the more it becomes like a manufacturing robot. There's a limit where it's just doing the same thing over and over and over again. Well, if you can predict everything about the way it will work.
Someone could be highly creative and therefore unpredictable, but they're predictable within a sort of distribution. Like, they're going to do something really creative, right? So there's being predictable doesn't mean being like boring and robotic. And it comes back to this probability versus Newtonian mechanics. So you're predicting the probability distribution.
Yeah, I do. I don't know if I agree because you got a robot on your floor and it's supposed to be doing something, right? Like a humanoid. You don't want it to just all of a sudden say, screw this, I'm going to go get a sandwich, which is like what a person might do, right? You want it to keep working. Right. So how did you make it be like that? Well, you set some constraints in the way that it's functioning that, well, okay, you're not going to just do whatever the hell you want. You're going to do these things at this time and so on. So this tension between what you could call the creative urge and the urge and just do what I tell you is always in the commercial side of these machines, always going to defer to the do what I tell you.
Well, where I stand on that is I want to build a cognitive architecture that has a parameter you can tune for that. So if you want the thing to just be totally do exactly what it's told, which by the way is not a good thing, because if you have a system that only does exactly what it's told, you need to micromanage it. So there's this, and you find this with people too, right? If you have someone that has absolutely no creativity or ability to interpret what you mean and then turn that into actual actions, you have someone that you have to literally tell them every tiny single thing every second of the day. So you don't want that. So you want things that are able to explore and make decisions on their own within some boundary, but you can also tune that. So I want to build a system where you can tune it everywhere from you have to tell it exactly which like instruction to do when, like pick up this, put it there, go to here, all the way up to you just give it a very, very, very high level goal, like do some work for Sanctuary and make the world better, right? And then it can do that. So I want to have a system where you can tune that parameter, not one or the other. Depends on what the task is.
Yeah, that makes sense.
Right.
Mm-hmm. Okay, cool. Well, I think we got through what I wanted to talk about mostly, which was this idea of the experience machine.
Maybe let's summarize. So you built a radio station.
Yeah.
It involved a whole bunch of different generative AI components.
Mm-hmm.
And then this was very interesting because we started thinking about how all these AI components relate to robots and whether you can collect enough data from robots to actually create something like a equivalent of a radio station, but it's a person operating inside the robot autonomously.
Yeah, although it wasn't, the causal link wasn't really that way. I've been thinking about this.
It was in my mind.
I've been thinking about this data-driven thing for a while now. I think that if there was a link, it was the neural tokenizer for audio.
Right.
Because there is an open question about what kind of data can you symbolize or tokenize? Is it like any kind of data? Mm-hmm. I actually think that in the natural world, like, the world of physics, the reason why you can tokenize everything is underlying structure and it's simple. Mm-hmm. So that was the primary lesson of the convolutional neural net and visual stuff, is that everything looks really complicated, but it's not really complicated. It's formed of building blocks. Mm-hmm. So it's a question if all data is like that, like human-like data. And I think the answer is yes. Everything is formed of simple building blocks. And if that's true, then these neural tokenizers are essentially learning the structure of the world, the simple structure of the world. And then when you've learned the simple structure of the world, then you can use the simple structure of the world to build on, your data-driven models, not the apparent hideous complexity of everything.
And you also see this with motion planning. So we talked about, learning motion planners versus solving the problem in a fully general way. When you learn motion planners, the best way to do it is to learn eigenmotions. So it's this. The human body doesn't move in completely random ways. It does certain things, like imagine reaching out and grabbing something. This is kind of a motion that is like a principal component that you find in the data, and then it's sort of just parameterized a little bit. So rather than starting in the dimensional space of all your different joints, so imagine you have 70 degree of freedom robot. You now have kind of you kind of tokenize in that space. That's a really dumb space to tokenize in, because what you're saying is there's no dependency between any of those joints. They're all independent essentially, and I have to predict them all independently. But what happens is you can change the space in which you're operating to one where instead of each individual joint being a dimension, each individual motion is a kind of dimension, and you can actually reduce the dimensionality of your motion planning space by using these eigenmotions. And here we have like the concept of eigengrasps, which are like the sort of primary ways in which the hand moves. And that reduces the dimensionality of the hands from 38 or 40 degrees of freedom down to maybe 5 to 10 or something like that. And you can do the same thing with the whole body motions as well. So this concept of eigenmotions is very similar to some of the concepts in reducing dimensionality of vision and audio.
Yeah. So that was the link for me between the two things, was the tokenization of audio.
Mm-hmm. And haptics too. I mean, we don't really understand it yet, but there's probably like eigen haptics or eigen touch
Sure.
building blocks as well.
Yeah.
Like all this touch sensors all over your body don't just get triggered in random ways. It's not like a random pattern.
Yeah.
It's very, very structured.
Yeah.
And you can reduce the dimensionality of that structure
Yeah.
a lot. Yeah.
Yeah. So there's going to be more on the 100 Years of Data project. We'll as we unroll it, we'll probably write it up and talk about it a little bit more publicly. But I think it's the beginnings of what is going to be the way that AGI happens. So I think we're close to being able to have a legitimate, like the first time ever shot at creating a real general intelligence in software. And it's all going to derive through learning over the data from humanoid robots. So that's the premise. It's always been the premise since we started this, more than 10 years ago. But now it's becoming something that is technologically feasible, or as close anyway.
Sweet. Well, it sounds very exciting. I'm looking forward to
this
future of ours.
Yeah. Well, we gotta get there as soon as we can.
All right. Well, let's stop talking then and go and do it.
Go build some stuff.
Yeah, let's go and build some robots.
All right. Sounds good. All right. Thanks, Suzanne.
Yeah. Thanks, Geordie.